So yeah, basically, I mean, now we're in multiple variable functions, everything gets that bit more complicated, both in terms of the amount there is to do and also the variety of what you might have to do, which is why the chapter on derivatives was so long, because there's so much to think about with derivatives. Well, same thing is going to happen with the integration equivalent. So think back to Calc 1. We'll still keep tracking these. Well, we don't forget at its heart, there are two very distinct concepts to integration. And the fundamental theorem of calculus often makes people forget that. But there's these two things. Right. Now, it's always incredibly frustrating in Calc 1, partly because, you know, people often come out of high school thinking that they know calculus. They'll come up to you and say, well, why am I in pre-calculus when I've already done calculus? And when you ask the questions, you find that by doing calculus, what they mean is they know the power rule. I mean, they basically come out of high school knowing that the derivative of x cubed is 3x squared, and that's it. They don't know what that means. They don't know why it's 3x squared. They couldn't find the derivative of any other kind of function, but in their mind, they know calculus. But because they've been kind of drip fed a few things at the start of that, it kind of gets in the way of full understanding sometimes in Calc 1 of what's going on. And in particular, the fact that there are two very distinct concepts here, right? The first one is the concept of the antiderivative. The idea of being given a function and, in effect, reconstructing the function that would differentiate to it. The second one is the concept of finding the area under a curve, or at least it's introduced with the idea of finding area under a curve. Now, they are completely different things, right? I mean, for examples, you know, the first one, I could ask you, what is the integral of 8x dx? And you would say what? Plus, okay, thank you. That's about to have palpitations. Because I can't fully recover the expression because I don't know what constant was intended. Any constant would do it, right? The idea of plus c being it can be literally any constant you like. There isn't one antiderivative. There is a whole family of antiderivatives, but structurally they're all the same. And then I also have the idea of the integral of from 0 to 2 of 3x squared, which I would say is x cubed evaluated from 0 to 2. But you only need to look at those two answers to see they are completely different things. One's a function and one's a number, right? When you actually evaluate them, you don't really, once you look at the answers to them, it's not really a surprise to say that they're completely different concepts. But the fundamental theorem of calculus unites the two in that to do this here, we needed to know the antiderivative of 3x squared, which became x cubed, to then facilitate the answer. All right. But it's always extremely frustrating in Calc 1 to bring the fundamental theorem of calculus out, which actually says that two completely different concepts are very closely linked together, and everyone's like, either completely underwhelmed or like, oh yeah, we already knew that. But it is remarkable that the area under a curve and the antiderivative of a function should in any way be linked, let alone that closely linked. All right, but throughout calculus, throughout Calc 1 and Calc 2, the concepts of antiderivative and definite integral have existed side by side, frequently kind of interchanged. You know, I mean, when you go back in Calc 2, when you do the partial derivatives and the integration by parts, that chapter, trig integrals, the homework question will just come freely interchange these two things. You know, you'll see one question which is a definite integral, one which is an indefinite integral. Because back then, all they're really trying to give you is, you know, procedural practice. But it almost is a negative in that it distracts you from the idea that you're dealing with two different things. And they shouldn't be conflated together. Well, that means in Calc 3, when we come to multivariable calculus, we're going to have to deal with analogies of both of these things. All right? You've got the antiderivative, and you've got the definite integral. Now, the definite integral used to mean area under a curve. But of course, now, area under a curve is going to become volume under a surface, right? Because everything's being stepped up. So the ultimate idea of the definite integral now is going to represent physically volume underneath the surface. Although there are other things that we'll get to in the process as well. Area still plays a role as well as other things as well. The indefinite integral, well, we'll kind of scratch the surface on that, but frankly, chapter 15 is really more interested in the indefinite integral, the antiderivative idea, because of the difficulties involved. Let's kind of think about what we've been saying. You know, if in the last chapter, let's say we've got something like this. That's a multivariable function. What's the partial derivative with respect to x here? Right. Well, ever since we started doing it, the concept of integration as an antiderivative has always just been reversing that process. So what, you know, this was chapter 13. So chapter 14 is naturally going to be interested in the opposite process. Instead of doing the partial derivative with respect to x, now, we don't use the phrase partial integral. You don't actually use that phrase, but in effect, that's what we're talking about. But if I consider the integral of this expression with respect to x, now, the implication of that is that, just as we were in the previous chapter, that we're treating y as a constant, although you don't see the partial derivative notation. Notice this is still dx, not that kind of partial d that we introduced in the previous chapter. That you'll never see this. Right, that's a meaningless notation. We're doing things slightly differently with antiderivatives. But the implication of that, if this is a multivariable function, is that just as before, you're going to treat everything except your one variable that you're integrating this time as constant. But if I do that, well, if I integrate 3x squared, I will get x cubed. If I integrate y, which I'm treating as a constant, I'll get xy. And minus 1 becomes x. But the tricky bit is the temptation is to write plus c, right? But don't forget what plus c represented. Plus c represented the most general thing you could write whose derivative was 0. Right? But now the most general thing I can write whose derivative with respect to x is 0 is not a constant. What is it? It's a function of y. Any function of y. I mean, y would do it, but any function of y as well. Because notice, if I write plus c here, I'm not recovering the original function. I'm trying to reverse the process, so I'd like to come back to this. Well, I've got my x cubed, and I've got my xy, and I've got my minus x, and my plus c could be the 3, but what's happened to the y squared and the 2y? The fact is, they need to be accounted for as well. So what I'm recovering is not a constant now, it's a function of y, right? That's the most general thing whose derivative with respect to x is 0. And so once you move into multivariable calculus, you basically, I wouldn't say you don't see plus c anymore. It shows up further down the line. But at the first stage, you're now not getting an arbitrary constant of integration. You're getting an arbitrary function of integration, right? It's an unknown function rather than an unknown constant. Now, that can be a lot more complicated of an idea. Because it's true that if you get plus c, all right, well, it could be 5, or it could be 12, or it could be -9, or it could be 5 trillion. Yes, there are an infinite number of possibilities for plus c, but they're all at least numbers. This thing here, this could be y, or it could be tangent y, or it could be e to the power y squared, or it could be y to the power 7 plus 2. I mean, there's like an infinite number of these, right? I mean, I could have, this could be 2y cubed plus y minus 5, or it could be natural log of y plus 1, or it could be e to the power of y minus 7. I mean, and plus 7, minus 15, they can all be in there as well. So even for this thing alone, this would be minus 5 or plus 2 or minus 8 or whatever. So within each function, you've still got that plus c idea. So it's like, I mean, it's hard to say that there's even more because there was infinity of them in the first place. So you can't really have more than infinity, but in another sense in math, you can. All right, later on in the math sequence, you'll start to look at how you can have orders of infinity, and this infinity isn't quite as big as this infinity. And right now, we don't need to worry about that, but that's kind of a part of the deal. So like I said, really, this kind of thing doesn't come along much till chapter 15. It does show up a little bit in chapter 14, but chapter 15 is a bit more interested in the antiderivative concept. We're going to be thinking about the definite integral equivalent. All right, but do notice, let's take two examples of that. Let's imagine we're doing the integral of 2x plus 1 minus y from 1 to 2 with respect to x. By the way, notice as well, I could equally have asked you to do that with respect to y, and then you would treat x as a constant. Now, the good thing here, of course, the thing I'm helping myself in terms of here is when you do the definite integral, you don't bother with plus c, right? Because it disappears anyway, right? If I integrate this with respect to x, I've got x squared plus x minus xy between 1 and 2.
Is the 1 and 2 still in row set?
Yes, yeah, they're always, whatever you've integrated with respect to, they are representative of that. And so what I get here is 4 plus 1 minus, sorry, let's try that again. 4 plus 2 minus 2y minus 1 plus 1 minus y. And so I'm going to get 4 minus y. Notice my answer, of course, is a function of y, not a constant anymore. In effect, and this is a very useful thing to keep in mind in this chapter, because it's going to become more and more common. If you integrate a function with respect to a variable, you remove that variable from your expression. Now, back in Calc 1, functions only depended on x. So if you remove x from that, all you're left with is a constant. The only thing left is a number. And so back in Calc 1, definite integrals, the answer was 12 or pi or something like that. It's the numerical answer. Here, if you remove x from a function of x and y, what's left is a function of y.
So then when you do it again in reverse to y?
Well, we'll get to that in a second. Yeah. Notice again here, if for some reason I decided I was going to incorporate some unknown function of y, the reason I don't bother is that's got nothing to do with x, right? So x being 2 and x being 1 isn't going to change anything. So I've left enough room in this. So whatever function I chose, when I subtract them, they'll disappear. So the reason I don't bother with the plus c, or now the plus some constant function, some function of y, is that it's going to disappear when I subtract the 2 anyway. So you might as well not bother with it in the first place. But, and the second thing before I get to it is, don't forget, we're treating y as constant, which means that actually the limits can involve y as well. Right? It's equally possible for me to have something like this. Now, the limits can't involve x, right? Because remember, the limits are represent back in Calc 1, they represent where your variable starts and where your variable ends. Well, that means that your x can't start at x because that's conflating. You're trying to use the letter for two different things there. But you know, now we're working in the plane and working with multivariable calculus. X can start at 1 and finish at y plus 1. Right? That's completely okay. So in this particular case, I would have x squared plus x minus xy. And so I'd finish with y plus 1 squared. Oh, sorry, I meant to write with respect to x. I'm sorry. What I wrote made no sense. I couldn't have dy and then also have y involved in the limit. Sorry, I just wrote it down wrong. Plus y plus 1 minus y plus 1 times y. That's my top limit introduced. And then I'm subtracting 1 squared plus 1 minus y. So notice there's a decent amount of algebra now to clean this thing up. But I've got y squared plus 2y plus 1 plus y plus 1 minus y squared minus y minus 2 plus y. Well, y squared minus y squared cancels. Minus y plus y cancels. Plus 1 minus 2 cancels. So actually, having done all that by coincidence, this thing ends up being nice and simple. But it perfectly well could have been something more complicated. But the point of this is now that the answer to a definite integral won't be a numerical value. It will be a function of whichever variable is left, the one I didn't integrate with respect to. Okay, does that make sense? Happy with that?
Yeah.
Let me just rewrite that on the next screen. So we just had that the integral from 1 to y plus 1 of 2x, is it plus x minus y? 2x plus 1, thank you, minus y. With respect to x is 3y. But if those two things are equal, notice it is now, and this is what you were just asking about, Asher, I could now, might be better, I could integrate this thing with respect to y from, let's say, 0 to 2, which is the same as integrating this thing with respect to y from 0 to 2. And so I will get 3y squared divided by 2. In other words, 3 times 4, so 6 when I divide by 2 minus 0. So 6. This thing on the left is what's known as an iterated integral. It's basically two integrals, one after the other, but with respect to different things. Now, iterated integrals basically only really exist in any meaningful way when they're definite, right? We're not going to see it. It's not entirely true to say it's impossible to come up with or to consider the idea of but generally it doesn't mean much. But if there are limits on the integrals, that's what we really think of as an iterated integral, and that's going to be what chapter 14 is mainly focusing in on.
Is it possible, instead of the conservative, to do like 0 to x?
Right, well, so
Isn't that a constant?
it kind of depends on the order that you do it. Now, notice here when I've written this, I haven't actually put in a bracket like I did at the top. And actually, this is the more common way of seeing it, except with limits. So let me just get rid of this. But here's the kind of thing that you're likely to see. Now, at the top, I did dx dy. In other words, I integrated with respect to x first, then y. It's perfectly possible, of course, to do it the other way around. There's really no reason why I couldn't have integrated this with respect to y first, then x, except that my limits precluded it here. Because if my limits involve y, then I can't be, that definitely means I'm integrating with respect to x. On the other hand, if the limits were constants, I'd be okay. So this can be either dx dy or dy dx. And we'll be seeing both, and we'll be talking at length about which one it is and why. Is what? Oh, it matters, but it could be given to you in either order. Yeah, but frequently the order is very important. In fact, there'll be huge amounts of time and questions devoted in this chapter to the fact that you might want to change the order of integration and how you do that. But we haven't got to that yet. Right. So I'm not going to do the same problem. I'm just saying you might get something like this. Now, the first thing that's happening here is that I'm integrating that function with respect to y, which means that these limits could be constants, or they could be something to do with x, right? This could be g of x and h of x.
But it can't be like g of y, h of y.
Not the way it's written here. No.
I'm talking about.
Just give me a second. I know where you go with this, Asher. I need some time to get there. All right. The outer limits need to be constants. Right, there's no two ways around it, because ultimately, by the time I've integrated this function with respect to y and subbed in my limits, this whole thing here now is just a function of x. So the second question is basically exactly where we were in Calc 1. Right, it's like a Calc 3 problem buried inside a Calc 1 problem. Or you could instead have the same function, but this time I could be integrating in the other order, which is fine, but this case the inner limits would have to be functions of y. Again, those functions could just be constants. The inner limits could be 2 to 6, that would be fine, but at the most general, they can be functions of y. So this could be a function of y, g of y and h of y, and again, this would be constants. Those are the two kind of things we're going to see, and the question could just as easily be one or the other.
Are we doing 3 variables?
We'll get there. So what 14.1 kind of introduces this idea and gives you some practice of doing it. 14.2 very quickly reinterprets this as what we call a double integral, which is very closely related to it, and we'll be talking about how it is. Then down the line is a triple integral, and that's when we get to functions of 3 variables. And in theory, you could keep going, but these things have very practical uses. It's hard to imagine a practical use to a 4 variable case, so we don't bother with that. Okay, but essentially what's going on here is integration processes, two of them put together. First one, you're treating one of the variables as a constant. Which variable you treat as a constant will be determined by which order this comes in. Second one is just a standard Calc 1 situation. Okay, so that's the kind of setup that we've got for that. So see if you can evaluate this. Is what? Yeah, my pencil's getting a little charged. Now, you tell me, am I going to have to write dx dy or dy dx? It's got to be dy dx, right? It wouldn't make any sense to write it the other way around. See if you can evaluate that. So if I integrate this with respect to y first, what do I get? Three x squared y squared, and that will have limits of 3 and x plus 4. So I need to plug that in. So I've got 3x squared times y squared, which will now be x squared plus 8x plus 16. Minus 3x squared times 3 squared, so minus 27x squared. Right? I'm happy with that. So if I clean this up, this is now 3x to the power 4 plus 24x cubed plus 48x squared, but then minus 27x squared. So plus 21x squared. Notice at this point, we're now back in pretty basic Calc 1 territory to finish up. All right, so what do I get? I get 3x to the power 5 divided by 5 plus 6x to the power 4 plus 7x cubed from 0 to 2. So that's 3 times 32, so 96 over 5. Plus 6 times 16, so 96, plus 7 times 8, oops, no, that'll be 56. Minus 0, so whatever that is. Right. I mean, this last bit is very trivial in terms of getting your head around the ideas. Does that make sense? Let's think about what this actually represents, because a major part of this, remember back when you were integrating in Calc 1, when I integrate between 0 and 2, for example, what I mean is on the x-axis, the interval of the x-axis is between 0 and 2. And part of the interpretation was the area underneath the curve between those two values. So let's just think about what's going on here. In this particular case, the inner integral is telling me that basically y is going between 3 and x plus 4. So let's think about what they look like. Y equals 3 looks like this. And y equals x plus 4 looks like this. Right? So y is varying between those two things. In effect, y is sitting between these two graphs. It's going from a lower limit of 3 to an upper limit of x plus 4. Of course, whereabouts on the x-axis it is depends on where it reaches. But then it's also telling me that x is running from 0 to 2. So on the x-axis, I've got 0 and 2. So in effect, what I'm having described here is this region of the plane. This problem is associated with that region of the plane, right? Y is varying between a constant value and a changing value, and then x is stuck between two constant values. The way this is going to be interpreted, I'm kind of slightly jumping ahead to section 2 here, but we'll be getting to it tomorrow anyway, is this region of the plane is known as R. And I would write this as what we call a double integral. And so where we're going with this, and again, we haven't quite got there yet. You know, we've still got a bit of section 1 to talk about, and you've got questions. But to try and frame where we're going is, eventually questions go like this. This is known as a double integral. This is an iterated integral, but you basically turn any double integral into an iterated integral to actually evaluate it. But your limits now, just like it used to be an interval on an axis, is now a region on the plane. Because remember back in the previous chapter, that was the new version, right? What used to be written as an interval for a domain or range or whatever, then became drawn as a region on the plane. Well, the region on the plane will be represented by this value R, and the question will have to describe to you what that is. It'll either draw it for you, or it will tell you in descriptive terms what the region R is. dA we'll worry about when we get there, but dA basically, it's not too hard to imagine. It's either dx dy or dy dx. Right? Which one it is, well, that's part of what we're going to talk about. Now, what we're going to look at, and this, when you go through section 1, it does get talked about in the book, and what we're going to talk about in a lot more detail later on. Cast your mind back to volumes of revolution, this method and shell method when it was done. You remember how sometimes you use vertical strips and sometimes you use horizontal strips, right? Same idea is going to show up here. In this case, we're basically using vertical strips, right? Because the vertical strips themselves have a lower limit of 3 and an upper limit of whatever the y coordinate is here, which is x plus 4. And then we look at how many vertical strips there are. And if you think back to when we've done this in Cat 2, you'll see that this ties together quite a bit. The alternative is you might want to consider horizontal strips. Now, in this case, that would be a bad idea, because horizontal strips, some of them go from 0 to 2, but some of them go from this line to 2. And again, if you think back to this method and shell method, that was a way in which you made a decision on which one was better. All right, but let's imagine I'm going to change up the question rather than still use this one, where I can show you greater kind of symmetry to this. Let's imagine that I had this question. To some extent, right now, the function itself doesn't matter. I mean, that's going to determine the answer, obviously, but the thought process I want to particularly focus in on is nothing to do with the integrand and everything to do with the region. So let's imagine right now the region I'm interested in is this. So this is 1, this is 3, this is 2. So this is our region. One thing you'll notice is when you're shown a region, especially if it's drawn for you, you're going to have to work out for yourself what the lines involved are. So you can see here that the 3 lines involved for this region. One is the x-axis, so y equals 0. One is the line x equals 3. What is that straight line? So it's y equals mx plus b. What's the slope? 1. Right? Rise over run is 1. So it's y equals x plus or minus something. What is the something?
Minus 1.
Minus 1, right? Either you can work out where it goes to here, or you can just call it contains the point 3, 2. So when x is 3, y is 2, it has to be minus 1. Right? That's the only way. Or you put in 0.10. Either way. So my 2 options here. Option 1 will be to rewrite this dy dx. Now, if we write it as dy dx, the first thing that's happening is I'm thinking what is y vary between. Right? In other words, this is vertical strips, because I'm asking y goes from what to what. Y varies in vertical direction. So the lower limit of y is always 0. The upper limit of y changes because it's on the line, but it changes because it's x minus 1. So in this case, it will be the limit from 0 to x minus 1. Then what will x vary between 1 and 3? Now, does that make sense? Because this is really part of most of chapter 40. Now, the latter stages are triple integral, where this won't be a region of the plane, it will be a region of space. But obviously, if you understand this bit, then that's not over-dimensional, I guess, still regions. Right, so that's one option. Option 2 would be instead function. This time I decided to do dx/dy. Now this will be associated with horizontal loops, because the first thing that's happening is x is changing from further left, further right. Exactly. Now, and again, it's back to the challenge. If I want x over here, remember, I can write this, these limits as a function of x. These limits have to be a function of y. So I have to rearrange the equation so that x equals to do y. Of course, in this case, it's an easy just 1 plus 1. In back to this method, sometimes that's much more difficult up here. Sometimes it determines which one to go. In this case, x is going to vary from plus 1 to 3. What will y then vary between 0? So your question is, does the order matter? Yes and no. I mean, you can quickly whichever order you want. It's not the case somehow limits get switched around. As you change the order, it has an effect on what the limits are. Right? Notice the fact I switch the y the x around in no way somehow switch the limits are. The limits got completely redesigned from the ground up. So what do you care about ordering? Well, like with this control method, sometimes one of the curves might hold easier to write y as a function of x, x as a function of y, vice versa. That might really load you toward choose one of these over another. In this particular case, in this problem, you obviously don't really care. They are literally going to be exactly the same level of difficulty. But in amongst your homework, just try evaluating this with any function you like. You know, if you want to pick, you know, this function could be xy, or it could be 3x plus 5y, or anything you like, literally any function you like, plug it into the first version with those limits and work it out, plug it into the second version with those limits, and you'll get the same number every time. Because you're evaluating the same thing every time, you're just picking one of 2 different routes to the answer. As I say, in this case, you're just replicating things. Later, it's going to be a case that we're trying to decide which of these 2 routes would be the better one. But until you've kind of got your head around just the basic idea of setting it up and doing it, there's not much point thinking about that. Last thing I just want to mention. Any questions on this? Just to sort of tie a very important concept in. Think back to Calc 1. If I wanted the area between 2 curves. So this is y equals f of x. This is y equals g of x. If I wanted that area back in Calc 1, I worked out the integral from a to b of f of x minus g of x dx, right? That was my formula. Notice now, I've got another way of writing that. Because if I integrate 1 with respect to y to get y and then sub in my limits, I'll get f of x minus g of x. All right. So basically, if I call this region R, then the area is simply the double integral of 1 dA. So now area can be redefined, and from now on will be redefined as a double integral rather than the kind of thing we were doing back in Calc 1. You needed it in Calc 1 as the sort of stepping stone, but basically from now on, area is considered a double integral. Just as by the end of this chapter, volume will be considered a triple integral. So that's what I mean when I said that this method and shell method stuff was really just a placeholder. Volume of anything will eventually be considered a triple integral, which is basically what we're doing now, but 3 times rather than just 2. But once you've mastered double integrals, triple integrals really aren't a big jump. So read through section 1, please. You know, there's a couple of things I haven't mentioned, but are shown in the text. But mainly you should be able to follow it all, I think, and then try some of the problems. Christian, I just wanted to mention something about the take home to you as well. But also I just want to stress to all of you, with this take home, make sure with this diagram you realize you are only creating this shape. Yes, it's a rectangle attached to an equilateral triangle, but you don't have to, there's no fencing required for this bit here, right? You're just building the perimeter of the shape. Otherwise that'll mess up. I mean, that'll be a different problem with different answers, but that's not the problem that you're given. So, okay. So you might want to redo that because I think you've incorporated that in.
Hold on, let me see that for a second.
But we're good. So yeah, if you guys want to go, you can go.